Hello guys, this is lesson 8. For the first time I'm trying to record it in the classroom, so I hope the sound will be okay, because there is a bit of echo when the classroom is empty. What we will focus on in this lesson is the traveling salesman problem. This chapter 5 has 4 sections. We will split it to 2 parts. 2 first parts, that means explaining the differences between classical and practical problem, and using a minimum spanning tree to find the upper bound. These 2 we will do this week, and the second 2 we will do in the next week video. So let's look at what the chapter is about. As you can see from the name of the chapter, it's traveling salesman problem. So it will relate to the problems when you need to visit several cities or several stores or several schools or whatever places. And obviously what you want is to minimize the distance or time, or obviously then cost as well. That's why solving this problem involves finding a tour of a minimum total weight. However, there is no efficient algorithm. What we can do though is to find out the upper and lower bounds, which will give us the interval where the optimal solution happens to be. So how it works is initially you find out the maximum possible number or the initial upper bound that the distance or time or cost cannot cross over. And also we will find out the initial lower bound that the cost or time or distance cannot go below. And then your task is to improve these, so you will find out the better upper bounds somehow, the way I'll show you in a minute. And eventually when you find several of them, you can find out which one is the best for you, or which one is the shortest, or that takes the least amount of time. And the same thing we will do for the improving the lower bound until we do not find out the best one. And once we do, these 2 values will give us the interval where our optimal solution happens to be. Okay? So let's look at the first section and comparing the differences between the classical and practical traveling salesman problem. Okay? First, we need to introduce the vocabulary. I think the first one, that means the first word called walk, we already had. It's the finite sequence of the edges such that the end vertex of one edge is the starting point or starting vertex of the next edge. If you make this walk in a special way, that it will be a walk which visits every vertex and returns to its starting point or starting vertex, then this kind of walk is called a tour, and that's what we wanted. And then again, if I make this tour to be a special, that means it visits every vertex exactly once, I am calling this tour an Hamiltonian cycle. Okay? So we have a walk, I think we had it before as well. Then we have a tour that is a special walk, and then we have a Hamiltonian cycle that is a special tour. So tour is a walk, Hamiltonian cycle is a tour. That means Hamiltonian cycle is also a walk. There are the differences between the practical and the classical problem. Classical problems is that your aim is to visit every single place, that means every single vertex, exactly once before returning to the starting point. The practical problem is if you visit every single vertex at least once before returning to starting point. And then if you have a practical problem, the same as a classical problem, if these 2 are equal, then the network was converted into a complete network of least distances. Now you probably might be thinking like, what the hell is the complete network of least distances, because it sounds complicated. So let's first look at that, and then later we will do the examples, because I think it's pretty easy when you see the examples. So when you look at the complete network of least distances, is a triangle. It's such a network that in each triangle of this network, the triangle inequality holds for every single one of them. The triangle inequality, this should be clear to you, and obviously the two shortest sides in the triangle, the sum of them is longer than the third side. Otherwise, you cannot construct the triangle. If it doesn't, then you replace the longest arc in those triangles by the sum of the two smaller ones. And this way, you will turn it into a complete network of least distances. And in such network, the classical and practical problems are the same. Now, table of least distances is basically the distance matrix that we already had a couple of weeks ago. But in this case, it's the distance matrix for a complete network of least distances. And that obviously shows the shortest path between any 2 points in the network. So I think it's easier than talk about it. You need to clarify the vocab, obviously, but once you clarify the vocabulary, then let's look at the example straight away. So the first example is asking us to create a table of least distances for the given network. So we have the network on the picture. What we need is the table. The top row shows you the shortest routes starting at A. Okay, now how to get it? You can see that from A to A, B to B, C to C, D to D, and E to E, obviously we have no distance. From A to B, I have several options how to get there. A to B is a direct link, 11. But remember, the direct link doesn't have to be the shortest link in these cases, right? So I could also go A to C and then to B, but that it would take me 40 kilometers or 40 units or 40 minutes or 40 hours, whatever. So obviously the shortest one is 11. From A to C, again, is the direct link, 13, but you can always check if there is not a shorter way. From A to D, it's 19 because you go to B and then to D, that's the shortest one. And A to E, you have several options. You can go 11 plus 8 plus 14, but that would be longer than when you just go A to C and then to E, what would be 31. So I will do the next one. B to A is obviously the same as 11, as was A to B. B to C, we can check B to C. The direct link is 27, but when you have, that's the direct link is 27, but you can also go from B to C through A, what would be 24. And then from B to D, the direct link is 8, and in this case, it's the shortest one. And B to E, we have several options how to get there. The shortest one would be 22 if you go through D. And then again, because B to C is the same as C to B, so that will be 24. And A to C is the same as C to A, so that's 13. Now you can pause the video if you want, and you can try to complete the rest. So C to D, the shortest one is 32, 35, is 32. And C to E, we have 18 is the shortest one. So I have CD, DC is 32. Then I have BD is 8, and then I have AD is 19. And then the last one, DE, is the shortest one is 14. So that will be 14. Then CE is 18. BD is BE is 22 and AE is 31. Similar story is here, except you are given not to fill in the whole table, just to complete it. And you have 6 post offices. The central office or sorting office is at point S, that means this one. And our task is to complete this table of least distances for the network on the picture. You need to stating your shortest route for each of the entries. So what I'm going to do is I'm going to look at the ones that are missing in the table. So the first one that is missing is SA. S is here, A is here. You can see the direct link is 13. But if you go through B vertex, then you will have 10. And if you go through F vertex, you will have 8. So that is obviously the best option because it's the shortest. SFA is 8, and you can put it directly to the table. So SA and AS is the same distance. The next one is SB. From S and B, direct link is 8. Through A, it's 15, but through C, so S, C, B, it's only 7. So 7, and then 7. Then the next one missing is SD. And SD, when you look at the picture, the direct link is 15. But you can go through C, that is only 14. So S, C, D is only 14 units. You could also check the other routes, but they would be longer. The next one is, so 14 is here, and 14 is here as well. Next one is SE. Now from S to E, you can go through D, what would give you 28, or you can go through F, what gives you 19, so that's obviously much better. S, F, E, that is 19 units. And that's here, 19 and 19. Next one that is missing is AC. AC, that's the shortest one. Well, you have several options again to choose from. The shortest one is going through B, so A, B, and C. You can check as well. So AC is 7 and AC is 7. Then the next one is BE that is missing, BE. But you can see here BE is 19, so it must be 19 as well here. And if you want to find a route, you have to find out the one that has 19 units or is 19 units long. So in this case, it would be B, A, F, E. That's 19. The next one is BF. BF, so from B to F, you can pass through S, that would be 13 units, or you can go through A, that is only 5 units, so obviously much shorter. BF is 5, so BF and BF. And then the last one is DF is missing from D to F. From D to F, if you go DEF, then it's 27. If you go DSF, then it's 20. But you can also go D, C, S, and F, what will give you 19. 19 and 19 here as well. So what you can notice about the table once you completed it and you look at it in terms of symmetry and you look at the diagonal here, then you can see the table is perfectly symmetric, right? This happens for the undirected networks, but you will only be asked to complete the undirected network. That's why you can be sure that you can use the symmetry to complete it, like what I have just done when I was using the information about the 19. So if I just delete this because I wrote a note there, or I took the note from the pictures, from the book as the reminder for you, so you can read the note as well. That's just what I said now. So let's look at the guided practice. We need to complete a table of least distances for the given network. Again, that means we don't have to create it from the beginning, from scratch, but we just need to complete. Remember, because we are dealing with a symmetrical undirected network, that means the table will be symmetrical. So let's look at the AB is 7, and then AC, it can be either 20 direct link, but there is a shorter one that's 10, and I'm gonna copy it directly here so I can save, I don't have to do it later. Then AD is direct link is 11, but there is a shorter one that's 9, and that's 9 here as well. Then I have BD, B and D, let me see, it's 11 is the shortest one. B and D is 11. And then I have BE. BE is either 12 or 15, so 12 is smaller. 12 and 12, and that's about it. In example 4, we need to describe the difference between practical and classical traveling salesman problem. So what does that mean is you just need to state what are the differences in written. So it's exactly what we said at the beginning. So in the classical, you can just say classical problem, or classical. If this is on the paper, on the final one, on the exam, then you just write it exactly as the definition told you. That classical means that each vertex must be visited exactly once. Exactly once. And if you talk about the practical problem, or practical, then each vertex must be visited at least once. That's the main difference. Okay, so the A case would be fine, finished. In the B case of this problem, they ask us to find out by inspection the solution of the practical traveling salesman problem, and in the second case is the classical. So that's why you need to know the difference, because if you are not sure which one is which one, then you either mix them up or you will not answer correctly. So in the first one, in the practical one, it says that you need to visit every single vertex, or you can visit every single, you must visit every single vertex at least once. So that's in the first case means at least once, in the second case exactly once. I'll start with the second case in the classical one because it's easier. Here it's easier. If I need to visit every single vertex exactly once, so in this case it's very easy because I can go from A to B, then to C, then to D, then to E, and then I come back to A. So when you count it together, it would be 2 plus 3 plus 9 plus 4 plus 8. It's 21, 24, this would be 26. If you look at the practical problem, that means you can visit the vertex more than once, but at least once you have to go there. And by doing this, you can shorten the total distance or total time that you need to travel, the total weight, okay? So in this case, in the classical, in the practical problem, then when you look at it, there are several options. For example, I can go from A to B, that's 2. Then I continue to C, then it's 3. Then I go to D, that's it's 9. Then I go to E, that's 4. Then I come back to C, that's 3. Then I go back to B, that's another 3. And then I go back to A, that's another 2. So together it gives me 6, 12, 21, 24, again 26. So in this case, I didn't improve my distance. However, there is another solution. If I go from A to B, that is 2, then I go to E, that's 1, then I go to C, that's 3, then I go to E, then it's plus 3 again, then I go to D, that's 4, then it's E, I'll go back, that's another 4, then I go to B, because, B, that was the shorter one, plus 1, and then I go back to A, and that's plus 2. So when you add this, 11, 14, 17, 18, and that's 20. And suddenly you see, even though I visited some vertex more than once, but it significantly shortened my time or my distance that I needed to do this. We were asked to state the route used in each case, starting from A, that's what we have done here, or here, and also here. So the next section is going to talk about the second point that we need to cover in this chapter, and that is using a minimum spanning tree to find out the upper bound. The algorithm for this part is very quick because you just need to go back to Kruskal or Prime's algorithm to find out the minimum spanning tree, because this will guarantee that every vertex is included. The second step is you will double the minimum, the weight of the minimum connector, because this will guarantee you that you will complete the cycle, that you start and finish at the same point. And the third step, you can improve your upper bound, that is called initial upper bound, by seeking possible shortcuts. Because using some of the non-included arcs can enable you to bypass a part of the minimum spanning tree that you have repeated, and that's why it helps you to shorten the initial, or to make the initial upper bound lower. So let's just look at example 5. In the first part, it asks you to use the Kruskal algorithm to find the minimum spanning tree. If you like, you can pause the video now and do it on your own, and then we just compare the answers. I will quickly do it. You can recall the Kruskal algorithm starts with the shortest edge. So in this case, I have number 3 is the shortest one, so either AD or AC would be my first one. So AD is 3, then is AC is 3. The next one is 4, what is CE? You have to make sure that there is no cycle being created. Then the next one is, it's 5, but obviously I cannot use CD or ED because the cycle would be created, so those two I skip. But the next one would be BF, that's 5. Then next one is 6, I don't have, I have 7, DF7. And then I have last one I still didn't connect is G, so what is GF is 8. So when you look at the tree, if you sketch the tree, it would look something like this. Then I have F, and then that's B, and this is G. So this would be my F, this is my B, this is my D, A, C, E, and last one is G. and the weights are, this is 4, this one is 3, this one is 3, 7, 8 and 5. Okay, so A case is fine. Now B case is asking you find the initial upper bound. Very easy. What you need to do is just to double the connector, the weight of the minimum spanning tree. So when the minimum spanning tree weight is 7, 10, 17, 25, so 30. So then initial upper bound is double this value. 2 times 30, what is 60? So this is the upper bound. That means that's the initial upper bound is 60. That can be maybe improved, but it's definitely the upper limit of your optimal solution. Okay, so let's look at the next one. Here we are presented the table of least distances for the network, for some network, and we need to find the initial upper bound for this one. So in this case, we're going to do exactly the same thing, except I am given the table. So that's why the primes algorithm would be much better, because I can apply primes algorithm on the matrix. Again, you can pause the video if you like, and then we will compare. So I will do it. Did they tell me where to start? They didn't, so I'll start, or maybe in the, no, they didn't tell me. So I'll start at A, because I can choose where I'm going to start. You can choose, you can start at any vertex. So A would be my first one. The smallest number in this column is 11. And I'm cancelling the A. So B would be, this is AB, is 11. B was my second one, so I'm checking A and B columns. The smallest number is 8, so that means B, D is 8, so that will become my number 3, but B would be cancelled now. So I'm checking in number 1, 2, and 3 columns. So the smallest one is 13. That will give me AC with the weight of 13. Then I have C goes out. And this is number 4. And I forgot to cancel D before. So the last one, the smallest one is 14 in this case. So that's E. And that's DE, that is 14. So minimum spanning tree weight, would be 27, 35, 46. So when you look at it, so this would be C, A, B, D, and E. So I have 13, 11, 8, and 14. Okay, so the initial upper bound, because that's the task that they asked me to solve, initial upper bound is 2 times the minimum spanning tree weight, so 2 times 46, what would be 92? Now, the real question is, if this could not be improved somehow by looking for the shortcut. Because what is happening, I'm going to change the color. So you will go from C to A, and then A to B, and then B to D, and then D to E, and then you have to come back if you want to start at C. Or you can start at A and you will go first to C and then come back to A. Okay, that's why it is doubled. But now the question is, if I could improve this initial upper bound somehow, and when you look at it, let's say I start at A, okay, and I could go all the way to E, But once I'm there, instead of going back to DBA, I can check if there is no possibility to pass directly from E to C. And when you look at E, C, they are connected. Okay, so I could do this. I can connect it, and that would be 18. So now the following question we could ask, that is not given in the example, but we still could look at it, is the question, how much did we really save by making this shortcut that we discovered that it's possible? So there are two ways how we can look at it. Either I'm going to start with the initial upper bound, that was my 92, right? And then I edit 18 for the CE arc or edge. But by adding this edge in there, what I saved was 14 and 8 and 11 and 13, because I didn't have to go back all the way to C or to A. So when you look at this, this should be 110 minus 25, 33, 46, so 64. Okay, so this is my improved upper bound. And obviously it's much, much better than 92. There is another way how you can look at it. If you start with a minimum spanning tree weight, that means 46. That covers already, if I start at C and I go to E, if I go like this, right, then I'm gonna get 46. And if I add 18 to it, that means I don't have to go all the way back, that also gives me 64. Whichever way you look at it, it doesn't matter, it's still the same value. So improved upper bound is 64. And there obviously is a difference whether you travel 92 miles or 64 miles, or whether, if it's in times, whether it's 92 hours it takes you to complete the journey, or it's 64 hours. So that's why improving the upper bound makes sense in terms of saving either time or distance, and obviously cost and money. Let's look at some guided practice. So we have again the table of distances in miles in this case. We have 8 cities. Politician must visit each city, and he or she starts at A and finish at A. And she of course wants to minimize the total distance traveled because it saves her time as well. And in this case we are given here, this is given already, the minimum spanning tree for this network. So we just have 2 questions left. In first, we need to find out the upper bound, and in second, we should use the shortcuts to reduce this upper bound if it's possible. It doesn't have to be always possible, so if it's not possible, your conclusion is just not possible. They give you the value under which you should push the upper bound down, okay, so below 1300 miles. So let's look at the table and the minimum spanning tree on this slide. The first case is very easy because all we need to do in the A case, if I want to find out the upper bound, I'll start with the initial upper bound. Initial upper bound is basically when you're going to add all of it, all of the weights of on the edges, so 47 plus 84 plus blah 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 blah, all of them, 155, and don't forget to multiply by 2. So in this case you're going to get 1502 miles. This is your initial upper bound. Okay, and now we're going to check if there is not a possibility that I could save going, because I'm going this direction, right? For now, I'm going from A to B, but then obviously I have to also come back to A. Then I go to C, and I have to come back to A. and then I can go to E, H, F, G, D, and then I would be coming back to G, to F, to H, to E, and then to A. So that would give me the upper bound, the initial upper bound, 1502 miles. Now, what I want to do is to see if I cannot somehow, improve it. And of course, you can notice something. If I start at A and I go all the way to D, you can check in the table that from D to A, I can go directly, right? Because there is an edge. So I could just go directly back to A. We don't know yet how much would I save. If this edge is shorter than the sum of the AE, EH, HF, and so on. But we can easily check, okay? So I'm going to add AD, and I'm going to check the savings, or how much does it saves. So I am adding 382, but I am saving 155 plus 144 plus 70 plus 131 plus 120. So when you calculate this, you will get negative 238 miles. That means you saved 238 miles, right? Saved. And there is another one. You can guess, you can think, you can say it aloud to yourself if you want. When you look at A, you could notice that I had to go AB back to A and AC back to A. But obviously, I can check if I'll pass from B to C if I'm going to save something. So BC saves, how much am I adding? So from B to C, it's 121. So I need to add 121. That would be plus because I'm adding it. But how much would I save? I don't have to go 47 because I don't have to come back to A. And I don't have to go 84 because I don't have to go back to A from C. So this gives you 120, 100, so minus 10. So that means saved 10 miles. 10 miles saved. Okay, so the tour, we're going to check. The tour would be, I'm starting at A, I'm going to E, H, F, G, D. Then I go back to A, and then B, C, and A. Or obviously you can do A, B, C, A, and then go to D and back. That doesn't matter. So now you have two ways actually how to find out the upper bound. You can either, or the weight of this tour, or the distance, or the time, whatever the unit states. So you can look at your tour, and you know that it covers every single vertex, right? So that means you will start with 751 because that's the minimum spanning tree weight. And to this one, you added 382, and then you added 121. What will give you 1254 miles? And that obviously satisfies the criteria from the problem because they said it must be below 1300. There is another way how to calculate it. So this would be the first one. The second one would be the initial upper bound. Initial upper bound, that's you got. That was how much? That was 1502 miles. But you saved 238 miles. And in the second case, you saved 10 miles. That means it gives you 1254 miles. It doesn't matter which way you calculate it. You can use whichever you like. So this is the improved upper bound. In this question, there is obviously not only one possible solution. When we're talking about the shortcuts, you have several of them that you can try. Okay? If you look at this picture, or you have it also in the book, there are several shortcuts you can try. So for example, in the first one, I can go from D, I can go directly to B, or from B to D. Okay? What will add first more, because it will add 402, but it will help me save at the end. When I'm going to look at the final length, it will be 1237, what is additionally 17 miles that I saved. Another option might be you go from D to F, and then from F you go to A. And when you look at this option, then the improved upper bound would be 1264. Okay? Or another one that you only would do the CD, okay? That would save additional 248 miles. So the length would be 1254, just what we had before. So when you look at these options, obviously, because the aim is to make the upper bound as low as possible, because then you reduce the width of the interval in which the optimal solution is contained. So if the condition was below 1300, then also our original solution is perfectly fine. But in reality, if you find out even better upper bound, or the value that improves your upper bound further, then it's smart and wise to choose this value, because obviously it saves time and money. So let's look at the last example. Now we have a council employee that is doing service to 5 sets of traffic lights. They are located at the A, B, C, D, E. This table shows the distances, again in miles, between the lights. And this worker starts and finishes at A, and of course wishes to minimize her total traveling distance. Finding a minimum spanning tree. So I'm not going to do it. Please pause the video. You do it, and I will show you how the solution look like. I would recommend you to use the primes algorithm for this one. And then we're going to talk about B and C and D case. Okay, so I am changing the color back to blue, and I am giving you the minimum spanning tree that I found, but I don't want to kill the time. This is, I found E, this is C, this is A, this is D, and this is B. So this is 11, this is 8, this is 11, and this is 7. So you should see something similar. Obviously, you can draw it differently, so they would be isomorphic, but the information should be the same. Okay. Hence, find out an initial upper bound. So that's also easy. Initial upper bound is 2 times weight of minimum spanning tree. So in this case, it's 2 times 11 plus 8 plus 11 plus 11 plus 7. So that gives me 37 to 74. So that's my initial upper bound. Now let's look at the shortcuts to reduce the upper bound to a value below 65 and stay the route. So I'm gonna do it here. Use the shortcuts. There are several of them, obviously, that you can use. So for example, I can go from E to B. From E to B, it would give me additional 16. So I'll use E, B as a shortcut. So I would go like this, right? and that would help me to save 11 and 7 and also 8 because I don't have to go back. So it would be 74 plus EB is 16, that's taken from here, but I am saving 8, I'm saving 11, and I'm saving 7 because I don't have to go back. So this will give me 64. And the root that I would use in this case would be A, C, E, B, D, C, and A. They told me the value should be below 65, so this would be perfectly fine. This is the case, right? To state the root given by your improved upper bound and state its length. So this would be 64. And you would be perfectly fine. But sometimes it happens, it would be over 65, so you have to look further. If you try the problem on your own, another option, obviously there are many. I also discovered this one. I can go A, like when I reach B, I can go back to A, okay, directly. So I'm not counting this now, but I would go back to A from here. So that means AB is 13. So I would have 74 is the upper bound. I am going to add AB is 13. However, I am saving 11, I am saving 11, and I am saving 7. So that's 22, 29, 16, so this is 58. So in this case, the root would be A to C, then you can go to E, then C, back, then D, B, and go to A. So in this case, it's 58. Another option possible would be to use AD and EB together. EB and AD. Okay, let me change the color or erase this. So when you have that, let me see, EB, so I'll go EB, and then I can also use AD. And you can double check what would happen. So we have 74 plus 16, this would come from EB, but I would save 8, 11, and 7. But when I'm in D, I need to add AD, it's 19. So adding 19, but that will help me to save 11 and 11, right? Because I don't have to go from DC and CA. So when you do this one is the AD. So if I'm not mistaken, I have done it in my notebook. So when you look at it, it should be 61, and the root should be A, C, E. Then you go to B, D, and A. However, the length is 61. What is okay, because it was supposed to be under 65, but obviously 58 is smaller by 3 miles. So that would be all for today. We covered both of the points. First, introduction to traveling salesman problem and difference between classical and practical problem, what you should know and you should understand. And the second point was to finding the upper bound of the tour that we are trying to find out in these questions. So please just practice these 4 questions, 1, 3, and 1, 4 in set 5A and 5B. And when you come to tutorial, we can either discuss your questions that you found out or you cannot answer, or you had some doubts, or further clarification is needed, or we can practice more or discuss more together. Don't forget, the solutions are in the back of the book. Detailed solutions are available online and also on this website, where you can find out the templates as well. Okay, I'll see you in the class. Ciao.